So a little while ago, I made a video where I reviewed some code that was sent in. It was this weird game called Skyward Scammer. Something to do with like stealing balloons. Anyway, that's besides the point. The point is that at the end of this like 2D game, there was like this kind of pseudo 3D scene that used like the track from the original Mario Kart game.
But also, what is this like 3D graphics, bro? This is cool.
Anyway, I made a video talking about optimizing this like pseudo 3D rendering because there were a few things that we could do to make the performance slightly better. But what I said was that if you want the biggest possible optimization that you can do to this, it would be to not do it on the CPU, but instead to move it to the GPU. Because we all know that GPUs are very good at rendering graphics. And so I was like, do you guys want to see how to actually move this to the GPU and take advantage of that extra performance and probably just wind up with it being like a billion times faster? And the answer was yes. So that is what we're doing here today. We're gonna take this weird game, this weird like pseudo 3D rendering, which is actually based off of one lone coder and his like little engine, and we're gonna move it to the GPU using this GPU compute project that I made a video about a little while ago. I'll have it linked up there. Basically, it's just a simple app to run compute shaders using OpenGL. So we're gonna be moving this from C++ and from, well, it'll still use C++, but from being like mostly done on the CPU using C++, we're gonna move it from that to running inside a compute shader using OpenGL. Now, the biggest thing that I probably wanna mention is that what I'm going to be doing here today is like literally moving this code, this C++ code that was written. This is actually my like slightly optimized version, I think, from that optimizing pseudo 3D rendering video that I made. I'll have the original repository linked in the description below. This is the Skyward Scammer, like original repository that I reviewed. In source is where this like pseudo 3D plain.cpp file is. And you can see that's like what the original rendering was. I changed it like a little bit, optimized it a bit. We're going to be working off of this optimized copy just because that's what I have here. Didn't really matter too much. What I'm going to be doing is taking this code and like showing you how to actually move it onto the GPU to get the GPU to do the work. However, if you don't like constrain yourself with trying to execute the original code and basically do this like pseudo 3D rendering this exact way, then you could of course just render this scene in 3D and that would probably be even better. But this video is meant to be more of like a how to optimize something by moving it to the GPU rather than how to reimagine like an entire project and change it completely, but get like the same visual result. Now, a lot of this code centers on math. And if you guys are looking for a resource to help you with math, then I highly recommend Brilliant.org, the sponsor of this video. Brilliant.org is an amazing website filled with lots and lots of really high quality content on various STEM topics. Computer science and math are two things that I think Brilliant teaches really well. They have these fantastic like entry-level computer science courses that really teach you programming in what I think is a really effective way, because they don't teach you a specific language, but rather they teach you just programming in general, how to think like a programmer, and that's so important. Their way of teaching is super fun, engaging, and interactive. You won't just be like watching videos, you'll be actually playing with widgets, dragging these things around, learning how things actually work by playing with them, which in my opinion is just a far more effective way to learn. But this visual interactive way of teaching really translates well to math, because math is just such a visual thing. Going from their basic courses to things like linear algebra and calculus, trying to learn these more advanced topics with the help of this visual, engaging, interactive way of learning helps understand everything tremendously. And Brilliant also has this fantastic 30-day free trial that you can use to check out their entire platform. Just go to brilliant.org/the Cherno, link will be in the description below, or you can use the QR code on screen. You can use that free trial to check out their entire platform and see if you like it. And if you do, then that link will also get you 20% off a premium annual subscription. Huge thank you to Brilliant.org, as always, for sponsoring this video. Okay, so the first thing we're going to do here is we're going to check out this actual repository, right? So I've got some instructions here. It's really easy. Uses CMake. These are the third-party dependencies that it uses. If you have a look at the CMake file, it will actually fetch those dependencies for you. So you don't really have to do anything. You just have to clone this and then follow these steps. Links to all of this stuff will be in the description below, by the way, including like this source file that we will be using. Now, since the original video that I made on this project, I have added one thing today just to make this project of ours actually work, and that is this load texture function that is inside the renderer. The reason why we need this is because the original project actually uses like the Mario Kart PNG and this like sky texture. Actually, let's come over here and grab these immediately. So this is the Mario Kart.png file and this is the sky texture. We need these, of course. So let's copy them. And then over here inside the root of our repository inside app, I'll just make a directory called assets and I'll paste them both into this assets directory. If you just clone that GPU compute repository and run it, you should see this, which is just like that example from Shader Toy that I demonstrated. This is just running inside a compute shader. And if we go over here into the app directory and then shaders, compute.glsl. This is the actual compute shader that's being run. Now, one other thing you can do with this is you can reload these shaders while the program is running. You can just edit the file over here so you can see it's outputting O, but we could make it output color, save the text file, and then press the R key, and it will reload that shader. So whilst you're working on a project like we are here, that of course is very useful because it just helps you iterate faster or debug. Can't forget about debugging. So what I'm going to do to begin with is let's just come over here and strip like all of this code. I'll just keep this color output. Let's just make sure this is working. If the shader doesn't compile, it'll just tell you in the console log over here. Now let's come back to the original project, this like Skyward Scammer game. Let's take a look at it. So first of all, I added a timer into here, which tells you around how long it takes to render. So like 9 to 10 milliseconds over here. And we are running in release mode. This is after my optimizations. I think it was something like, I don't know. I'm actually not sure how fast it is on this computer because this is a different computer than that video. But anyway, it was even slower than this. And I added this nice like fog over here into the middle just to like fade out into the horizon to make it look a little bit nicer. So the first thing I want to mention here is, first of all, this is a very small resolution, but also this like person and the balloons are not part of this at all. If we go to the function that calls that pseudo 3D rendering, which is this, you can see we're not timing the actual main guy or the balloons, and they're just being drawn as a normal texture. So I'm just going to comment that out. We don't care about that. Obviously, this is what we care about. And you can see the performance is not affected at all because we're not even timing that section. Now, the other thing I'd like to do is just beef up the actual resolution. So here the width and height is set to like 30 times 24. Guessing 24 is maybe like the tile size of the rest of the 2D game. Let's set it to 1280 by 720, which is what that GPU compute project is running in. So now you can see in release mode on a pretty beefy CPU, it is running very, very poorly, like 30 milliseconds. So 1280 by 720 is probably what we're going to be focusing on just because that's what we're running our compute project in. But of course, this is resizable, so this should work at any size. So the first thing that we're gonna have to think about here is how do we get those actual resources working, right? So we have Mario Kart.png and Sky1.png. Let's get those loading and let's just see if we can like sample them in our shaders. So the first thing we'll do is in main.cpp, I'm just going to load them as textures. So we have this function now, let's just call this sky, called load texture. And then that takes in a file system path. So where do we put it? Inside assets and then like sky1, I think, .png. So let's just hit F5, see what happens here. Okay, well, it hasn't complained about not loading it. That's good. I want to quickly point out as well, the one thing I think I did to my local copy was I actually changed the working directory. So you can see I changed it to solution directory, backup directory, and then app. Because by default, it will just be your project directory. And because we're using CMake, that's inside like this build directory. And unless you want to like copy your resources into that directory, which is a little bit annoying, I just like to set my working directory to be like the root, I guess, of the actual app folder, which lets me access assets and kind of keep everything clean here. Because the build directory, you don't want to permanently store stuff there since that's like a local thing. Someone will use CMake to actually populate this directory. And having like a post-build step that copies assets is also annoying. So that's my preferred solution. So let's also load the other asset, which is mariokart.png. And we'll call this ground because in the original code, we also had ground surface and sky surface. So how do we get these into our compute shader? Let's do that first and foremost. The load texture function, by the way, is really simple. This, of course, is just open source. It's on my GitHub. I'll have a link to it in the description below. This is part of that GPU compute project. All it does is it uses STB image to actually load the image file, and then it just uses OpenGL to obviously make a texture on the GPU and like even generate its bitmaps. OpenGL is very easy to use. It's very refreshing, to be honest. So in our shader, if we want to access those textures, we basically just need to create a uniform sampler 2D and then just give it a name. So I'm going to call this U_sky texture, and then we'll have a U_ground texture. Now we can also specify a layout binding equals and then whatever we want it to be. So I'm going to make this sampler be in binding slot 1, so texture unit 1 basically, and then this one will be in 2. So you can see this one's in 0. This is important because obviously if we want to access multiple textures, which we have kind of 3 images, 3 textures that we're accessing inside this shader, we actually need to have them in different slots. So we need to now map one of these like textures to an appropriate slot. With the one we're writing to, we're using GL bind image texture, which you can see is binding it to unit, which is the first parameter here, 0, right? So that's why we have binding equals 0 here. This is binding 1, this is binding 2. So we need to use a function called GL bind texture unit. And then you can see that just wants a unit and a texture. Very easy. So to unit 1, we will bind that sky texture. So sky.handle. And then to unit 2, we'll bind ground.handle. And that, guys, is just as simple as OpenGL is. It's amazing. We can now just like use these textures in our shader. So what I'll do is I'll set the color here to just be texture. So this is how we sample a texture. We just use this texture function. And then yeah, like use sky texture and normalized coordinate. Normalized coordinate is the pixel coordinate divided by the texture size. So it's basically a value between 0 and 1, which is what a texture coordinate is. So let's hit F5 and you can see we now have our sky. Now it is upside down. The reason why, I'm just going to put these side by side here. The reason why is because if we have a look at these actual normalized coordinates, so I'll set the color back to that, the bottom left is 0, 0. Typically with textures and the way that they're stored, the top is actually 0, 0. So we don't really care about the X. Of course, X is going to be on the left. But in terms of like the Y, in OpenGL, we generally like to go up like this, but images often are stored kind of going down. So you've got two options to fix this. You can either tell STB image to actually load it flipped, so flip vertically on load, something like that, or you can just flip the coordinate. Since we're already here in the shader, I'm just going to flip the coordinate. So we'll just write normalized coord.y equals 1 minus normalized coord.y. And if we reload this, you can see that flips our coordinate. And now if we go back to just displaying the image, it's now the right way up. I don't know if this is really technically the correct fix for this. Like maybe flipping it vertically on load would just be better. To be honest, it's been a while since I actually thought about this kind of thing deeply. So for those of you out there who have opinions, let me know in the comment section below. But I've given you both options. Now, it would be great to see our ground texture as well. So let's look at them both simultaneously. Why not? Let's have our sky sample over here. And then I'll also have a ground sample that samples the ground texture. And then I'll set the color to be a mix of them. So we'll do sky sample, ground sample, and then 0.5. So basically I'm just blending halfway between the textures. So you can see they're kind of both overlaid on top of each other, but the point is they're both working. That's all I'm testing. So if we go back to our original code, now all we have to do here is basically just like copy and paste it into that compute shader and then translate it, port it into like GLSL. Now, what you need to think about though, is that the compute shader that we're looking at, it runs once for every pixel. That's kind of how we've set it up. Compute shaders can run an arbitrary amount of times. It's up to you to control that. But because we're doing image processing, that's kind of the goal of this, we've set it up to run once per pixel. So you can't just like put these for loops into the compute shader. That wouldn't make sense. That would mean that every pixel would be running over every pixel. It's basically the inner contents of these for loops that become just like the normal main function of the compute shader. And then if we want the X and the Y variables that are like the for loop index, the for loop iteration, then that's what this like pixel coordinate is, which comes from the global invocation ID. So it does require like a little bit of thinking as to how to wrap your head around it. The other thing that's very important is we have stuff that's outside of the for loops, right? So specifically, we have like these trigonometry functions that are used to like calculate these far and near variables. We don't want to put this into the compute shader. I probably would not do that. Instead, I would just leave these as like C++. The other reason why is because if we just collapse this for loop, we also change world X and Y based on like the elapsed time. So that's what actually creates that like animation of us flying through the world. These are obviously persistent variables that are actually stored inside the class as members. So if we wanted them to like persist in our compute shader, we would basically have to like write them into a buffer, and that complicates things. So what I would suggest here is just taking the actual for loops and the contents inside that, moving that to the compute shader, then everything else can just be done in C++. This stuff is the heavy lifting anyway, not like this. So it's going to be totally fine for performance. Don't worry. Now getting variables onto the GPU in OpenGL is very, very easy. So let's like do that with the time variable as an example. So we need to create like a uniform float called time. And what we can do in like more recent versions of OpenGL is actually set a location for it. So I'll just write location equals 0. This is separate to a binding. If we go back to our main function, all I have to do is write GL uniform 1F because it's a single float, location 0 because we set it to 0, and then whatever value I want. So I'm going to use glfw get time, which is just like the current time in seconds since the start of the program. It's just constantly accumulating. And if I go back to here, let's just grab that time variable and maybe let's just add it to our sky samples coordinate. So that should just scroll our sky texture because we've got the actual texture set to repeat. So the wrap mode is repeat, and we're just going to like increment the coordinate so it will scroll the texture. And if we run that, look at that, the sky is scrolling. I'm telling you guys, OpenGL, am I right? Maybe no one else gets this, but it's just coming from like, you know, using Vulkan for the last 5 years or so. This is just crazy. It's almost like using Unity instead of making your own game engine. So time is actually a variable that I don't think we'll need because we've established that since this stuff is outside of the for loops, we won't be doing it inside the computator, and that's the only place where this time is actually used. But anyway, let's start copying this stuff over. Actually, the first thing I'll do is I'll come over here, grab all these member variables, and then back in main, outside of our while running loop, I'll just paste them in, and then I'll grab all of these. I'll probably just put this into like this compute section here, since that's the main, I guess, rendering part. Now, I could keep these as is. I'd probably be more inclined to use GLM instead of the standard C++ or C math library. It's probably not going to matter too much in this case, but I'll change it anyway. So this stuff needs to run first, and then it does all of this processing, and then you can see it actually does this world_x stuff. Now, this stuff can actually just go directly under it because fworld_x and y are used for these variables, and these are the only variables we actually use in the rendering code. Fworld_x and y are not used. They're just used to create these variables. Now, elapsed time kind of sounds like it's the elapsed time since the start of the program. It's not. It's a delta time because it wouldn't make sense to multiply this by elapsed time because that would mean that the speed would increase over time. Since like 1 second into runtime, it's 1, 2 seconds, it's 2. So if this is ever growing, then the amount that we increment by is going to grow exponentially as well. So it doesn't really make sense. I don't know why it's called elapsed time, but this is our delta time. So to set up some delta time real quick, because we don't have any here, we'll just make a last time, which I'll set to glfw get time. And then over here, maybe the first thing inside our while loop, we'll write float current time equals the same thing. And then we'll write float dt for delta time equals current time minus last time. And then we'll just update last time to current time. That's all you need to do. And we now have the delta time in seconds. In more professional situations, you might want to like limit it or set it to a max or whatever. We don't care about that. So that's it. It's ready to use. We can just paste that in here. And again, I will use GLM functions instead. So now let's take a look at the code that needs to run on the GPU, which is all the stuff that's inside the for loop. Now, the first thing you'll notice is that these variables are all used in here, right? All of these are used inside the for loop. And to be honest, that's the only thing aside from the textures that we need to sample that is actually coming into this code here, right? So we need our computator to access all of these variables as well as the two textures. Two textures are already done, so just all of these variables. How do we get them to the GPU? Now, the best way probably would be to use a uniform buffer because that way you can just have like a struct and you can set them out all up and it would be great. My little GPU compute program doesn't have the OpenGL code to actually create a uniform buffer, and I feel like it's almost unnecessarily complex for just this simple example. So what I'm gonna do instead is just use uniforms to get them to the GPU. Now, it would be a little bit annoying to create 8 uniforms because there's 8 floats. So instead what I'm going to do is I'm going to create 2 vec4s and just kind of pack them in there. So to show you what I mean, I'll just create a vec4 called like far or like ffar because there's f prefix for some reason. And then we'll set this to ffar x1, ffar y1, ffar x2, and far y2. So basically what that means is that .x and .y are like far x1 and far y1, and then z and w will be x2 and y2 respectively. And I'll do the same thing for near. Probably makes sense to have near first. We'll just replace far with near here. And that's it. So in our shader, I'm going to create 2 uniforms. They're going to be vec4s, obviously. We're going to have near and far, and I'm also going to give them locations. Now let's keep near as 0 and far as 1 because we've established that we don't need time, so we'll get rid of that one. And so over here, instead of using GL uniform 1f, we're going to use 4fv. V is like for arrays, or like basically it lets you take in a pointer rather than the 4f function, which will actually get you to take in 4 floats individually, which is a little bit annoying. So we'll use 4fv. So into location 0, we will take in GLM value pointer and then f near. Now to use this value pointer function, we'll have to include GLM GTC type pointer. And this also requires the count. So this is the amount of vec4s basically. So we just have 1. So we'll put that in, and then we'll duplicate this and put it into location 1 and obviously set our fFar variable. So now we should have all of this data on the GPU, and we're obviously sending it like every frame. Okay, cool. So now we just need to take all of this code. I'm gonna kind of line this up side by side and show you how I'm gonna copy this across. So I guess I'll just start from here. We'll talk about the X for loops because there's 2 of them. And also y kind of does window height divided by 2. So we'll have to talk about this a little more when we actually start implementing it. But for now, so we can get rid of, let's just put it over here. So with that code copied, let's start changing some of this stuff. So f sample depth is y divided by window height divided by 2. So half of window height. Now, y is what? Y is the current index of our for loop here. So in other words, it's like the vertical coordinate. And then we're dividing it by half of the window height. Now, the window height is just our texture size. So what I can do is I can use, if I want to keep these like as floats and everything, I can use f text size, which is our texture size in pixels, but as floats. So we can get rid of the float cast and just use f text size dot y divided by 2. And then y is going to be our pixel coordinate, not the normalized one, but the actual pixel coordinate. And that's why we're casting it to a float. Now, to cast in GLSL, you have to use like these old style casts, and that should give us our sample depth. Now, this is almost our normalized coordinate, but not quite, because we're actually dividing this by 2. So if you wanted to, I guess you could just use the normalized coordinate, but then multiply the y by 2. But I'm going to try and go for a more direct translation. Now, inside here, we start using these far and near variables. As we know, they're packed into near and far. So near x1 is just going to be near.x. Near y1 is near.y. x2 is z. And y2 is w. Just going to add some spaces here. So this is z, and this is w, and this is y, and this is x. And then for far, we just have far.x, far.y, far z, and far w. And then we use them over here as well. And that's it. That's basically that part done. So back to this then, we have the 2 for loops. Now, originally it was 1 for loop. I just kind of tried to make the memory a little bit more like the iteration through the memory a little bit more like continuous cache friendly. That's why I split it up into 2. However, the point of these 2 functions is very simple. It just samples either the sky or the ground. So depending on which for loop we're in, and then just draws that somewhere on the window. If you actually look at the code, they're doing the exact same thing. So we just need to copy like one of them and then just make it draw 2 things, and that should be fine. So let's grab this stuff over here and I'll paste it here. This stuff is my fog. So we're not gonna bother with that for now. And then I'll grab this code as well. So if we have a look at this code that we've just pasted in, this sample width is basically doing the exact same thing that we had over here with sample depth. It's just that it's not dividing window width by 2. So we can paste that code in, change this to x, and just have this be f text size.x. In other words, it's just our normalized coordinate.x. But we'll keep it like that to be a little bit more direct translation-y. F sample x just uses like f end and f start, which we created up here. F sample width we obviously have, so this stuff doesn't need any changing whatsoever. Get rid of this comment as well. Now here we're basically rounding it off, so let's just make sure that they're compatible casts with GLSL, and then we draw it. So drawing is just image store, obviously. So let's just write image store, output image. So pixel coordinate. So where are we putting it? This is where we're putting it. And these are the colors that we're setting. So m window height divided by 2 plus y. Let's create a little ivec2 coord. And this is where in the image we'll actually write our color. And you can see here that for the x, it's just x. So that's easy. It's just going to be pixel coord.x. But then for this, we have to calculate it slightly. Y will be pixel coord.y. So we'll add that in. But then window height divided by 2 is going to be text size.y divided by 2. Text size.y divided by 2. And this is an integer. Okay, so that looks pretty good. Now we need to know what color to actually draw. And for that, we need to figure out what we're actually sampling. So the plus y is the ground surface. And you can see we're sampling it at f sample x and f sample y. So f sample x and y we obviously have. So let's grab our sky and ground sample. I'll bring them both down here. And instead of using normalized coord here, we'll use f sample. We'll make a vec2 of f sample x and f sample y. Now, if we have a look at the sky texture, it's exactly the same. So let's just copy this and paste it in here. So we have our sky and ground sample now. So since this is our ground coord, let's actually write in ground coord just so that it's a little bit more clear. We'll paste in ground coord here and we'll just write in our ground sample. So now we're writing our ground sample, whatever pixel we happen to sample from the ground texture, at this coordinate inside our image. And we have to repeat the same thing for the sky. So we'll do sky coord. And if we have a look at the original code, then for our sky surface, we are drawing it into window height divided by 2 minus y. So that's the only difference. We're just subtracting it. So let's write that in and then paste in sky coord and sky sample. And that, I believe, is basically it. Now, the big difference here is that if you have a look at this outer for loop, it's dividing the height by 2. And then obviously it's drawing 2 pixels instead of 1. So we're iterating through our image. Instead of going per pixel and drawing 1 pixel, we're going per like half the pixels and drawing 2. So we still draw all the pixels that make up the image, but we just draw 2 at a time and we iterate through half of the pixels of the image, if that makes sense. We're not really doing that here. We're iterating through all of the pixels of the image, and we're still drawing 2. Now, I still think this will work visually. It's just we're doing like twice the amount of work as we need to. Probably not going to affect performance at all though, because it's going to be crazy fast. But that's one thing that we might think about optimizing if we need to. I mean, I probably would. Now, this color variable I think is no longer used, right? So we'll get rid of that. So yeah, let's just hit F5, see if this compiles, see if it works. Okay, so we have an error undefined variable y on line 33. Okay, yeah, y. So y is pixelcoord.y. So let's just paste that in here. F5. Okay, that did not quite work. Here's a mistake. So pixelcore.x we're using twice. This is supposed to be pixelcore.y. I don't know how I wrote that. Seems suspicious. All right, let's hit F5. And there we go. It's working. So it's obviously upside down. Now, again, that's because in the original code, we're kind of going from top to bottom, but here we're going from bottom to top. So the simplest way to flip this the right way up is probably just going to be to change the way that we do this pixel chord Y stuff, because ground chord and sky chord are where we write it into. So instead of like writing this pixel here, we just have to make sure that we write that pixel here. So we're just flipping the vertical coordinate of where we're writing the pixel into our output image. So I think if we actually just come in here, we'll make the sky be plus and the ground be minus and reload this. And there you go. We're now the right way up. Now you can probably notice here that it's running smoothly, unlike this version. But let's just like visually compare it. Oh, I forgot about the fog. Let's quickly add the fog in. So if we have a look at the fog that I added in that optimization video, it's just this. It's just lerping between the full value of that color channel and the original value based on the sample depth. So if we just copy this for a second, how should we do this? So we should do this for probably like the sky and the ground samples here. So I'm just going to use this for reference, but I think we should just be able to do this all at once. So if I do .rgb equals mix, which is like the lerp function in GLSL. So we're going to mix between full white, which is basically this, like, because we're doing it per channel, and then whatever sky sample.rgb is, and then of course f sample depth is the amount, and then ground sample. So you can see this is like easier to do because like this swizzling, and because these functions can handle all three at once. I mean, we could have added that function as well, but there you go. It's just built into GLSL. So that probably is it. Hey, there we go. Okay, so the other difference I'm seeing here is, I don't know if you can see this, probably. This is using nearest filtering, whereas this is actually lerping, like it's using linear filtering, which is why this looks smooth, this guy, but this looks a bit pixely. So what we could do, of course, is just go into the renderer over here inside our version and just set this load texture, set this to like nearest instead of linear. If you wanted the exact same result, which I think linear is probably better. So you can see now if we zoom in, we have that pixelated kind of nearest filtering. I'll just leave it on linear. I think that looks nicer. It's just harder to achieve because you have to do the filtering yourself when you're not using OpenGL or any GPU rendering API for that matter. But otherwise, you can see hopefully that I have pretty thoroughly and pretty effectively optimized this application and this specific scene within this application. So how fast exactly is this running? That is the question. I have my little timer over here, which is a gist on my GitHub. I'm gonna copy this, and over here inside our app in the main file, just up here, I'm just gonna paste it in. So we have this scoped timer class that we can use. So I'm just gonna put it into, you know what? Let's just put it into the entire application loop. So not just compute, even though we are dispatching it here and we're actually kind of waiting for it here somewhat, just to get rid of any potential GPU, CPU synchronization events. We'll actually put it at each iteration of the for loop. So let's do scoped timer. We'll call it timer main loop or something. And that's all we have to do. We can just drop it in. We are in debug, but it shouldn't really matter because we're running this on the GPU. And you can see that we are at 6 milliseconds. Now that's a lie. That's a complete lie. It's because we have vertical sync on. We are waiting for that VSync, and this monitor is running at 144 Hertz, and 1000 divided by 144 is about 6 to 7 milliseconds. So that's the number you're seeing. If we scroll up a little bit, the GLFW swap interval, we can get rid of that just by setting it to 0. And now the real truth is revealed. Isn't that insane? Isn't that absolutely insane? I think it might be even more dramatic if we actually have a look at like the FPS. So what I'm gonna do is write a really simple like FPS timer here. Int FPS equals 0. At the very end here, we'll just do FPS plus plus. And then maybe once we calculate this, let's do float FPS timer. So this will be like a little, I'll call it seconds timer. It'll just count up to a second. So seconds timer plus equals TS, which is our time step. I called it DT. Usually I call it TS actually. I don't know why I called it DT, but whatever. And then if seconds timer, so it's just accumulating that time. If it's greater than, let's just say or equal to 1 second, then we'll set it back down to 0. So it starts again and we'll set our FPS back down to 0. And what should we do with that? So whatever FPS it just accumulates, that's how many frames it managed to actually, that's how many iterations of this while loop it managed to do within a second. Let's maybe set the window title here. So we'll do glfw set window title. Now this one's a window and a C string. So let's do std string title equals computer, I think was the name it was. And then let's just set that FPS into there. And then we'll do title.cstring and we'll write in FPS. Okay, so if we have a look at this now, okay. Isn't that absolutely insane? We're still logging. Let me get rid of the scope timer and we'll run it in release, which I don't know if that'll make any difference really, because obviously we're doing the actual work on the GPU. Yeah, okay. It's a little faster. Okay, so this is, as you can see, hopefully, this is absolutely absurd. To go from this, which is running at like 25 to 30 milliseconds, which is about like 40 to 30 frames per second, to like over 7,000. That's why it's so important that you understand like the problem of what you're working on and the best tool or the best way to achieve that, because it's not about like, oh, how can I speed up my C++ code and tweak it a little bit to squeeze out every ounce of performance. Maybe the whole approach to what you're doing is just completely wrong and there's just a much better way to achieve the thing that you're trying to achieve. Always use the best tool for the job. That's super important. And I think this is a really great example of that. Now, would this be even faster if we didn't go through like compute shaders? In fact, we're going through twice as many pixels as we need to, as I mentioned, because, well, for each pixel, we're writing out 2. So that's not even necessary. I'm not even going to bother. That's a good exercise potentially for you guys if you want to try and speed this up even more by doing that, but it doesn't really need it. I will quickly say that I am on an RTX 4080 Super. So of course that is quite a powerful GPU, but I'm sure this would be pretty fast on, well, any GPU compared to a CPU. So would this be faster if we didn't render it using that algorithm, but instead we actually just drew like 2 quads or something in 3D space and rendered it, I guess, not pseudo 3D, but like kind of real 3D. I mean, it's all 2D in the end anyway, right? But you know what I mean. I don't know. Let me know if you want to find out. Maybe that's something I can do. Drop a comment below. I hope you guys enjoyed this video. If you did, please don't forget to hit the like button. If you have any other ideas for what I can like do to take this further, or if you're interested in other kind of GPU programming and optimization topics, then definitely drop a comment below. Thank you guys for watching. I'll see you next time. Goodbye.